All right, we can get started here today. Thank you for joining us. In this session, we'll be talking about dust, fume, and mist collectors. My name is John Daniel. I head up our engineering efforts here at Donaldson Company. We also have Amy Miller on with us today, who's our training manager. She'll be working behind the scenes and will be moderating the Q&A session at the end. We're going to start off today's webinar discussing the basics of dust collection, including fundamentals and calculations that pertain to collectors. Then we'll get into different types of collectors, filter medias, including the criteria and some sizing examples. And then we'll finish up at the end with everyone's favorite part, the Q&A session. For anybody that's not familiar with Donaldson Company, we've been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first tractor engine filter. Today, we're one of the largest providers of unique filtration technologies, producing high-quality filters and equipment. We pride ourselves on having a global reach and a local touch. Our world headquarters is in Bloomington, Minnesota, and we have about 54 manufacturing plants and 23 distribution centers around the world. As you think of questions throughout the webinar today, please feel free to put them into the chat box, and Nate and Alex will be happy to answer them towards the end of our session. And then during the webinar, we may ask you a few questions that you can respond with a thumbs up or thumbs down. You can access these by clicking the face icon at the bottom of your screen. So I'm pleased to introduce our featured speakers today, Nate Hildebrand and Alex Bozer. Nate is a sales associate with Pearson Arnold Technologies, who is our local sales office representing Donaldson in Minneapolis, Minnesota. He's been in the dust collection industry for about 15 years. He actually used to be an engineer here at Donaldson before making the move to the sales side in 2021. Nate has a mechanical engineering degree from University of St. Thomas.
Hey, thanks, John. Certainly appreciate it. Looking forward to the conversation, everyone.
Great. And Alex is an aftermarket sales manager here, managing a segment of our aftermarket sales team. We call aftermarket or filters. He's been at Donaldson for 13 years. He has a degree in automotive engineering technology from Minnesota State University in Mankato. And with that, I'll turn it over to Alex.
Thanks, John. I'm glad to be here and excited to present. So we would like to start out by asking you about your experience with selecting and sizing dust collection systems. Please select the reaction emoji that best aligns with your experience level. You'll see the little bar next to the hand. You can select, what emoji kind of matches your experience level.
Oh, looks like we've got some experienced folks on the line here. Some experience, very experienced, so pretty broad range.
Excellent. Thanks to all of you for participating. It's helpful for us to know your experience level as we get started. So let's start with the basics for those of you who are new to dust collection system design. I want to start off with why dust, fume, and mist control is important. There are a lot of reasons to control dust, fume, and mist, including safety concerns and hazards, improving air quality for workers, exposure control. We want to reduce potential dust in the breathing zones of the workers operating the process. Environmental concerns, we want to meet EPA standards for environmental air quality and outlet emissions regulations. And lastly, cleanliness. We want to address concerns about the overall cleanliness of the facility. At the end of the day, it's about sending workers home safe to their families. So let's look at a picture of a common dust collection system. In this case, there's a robotic welding cell. As the robot welds, it generates fume. The dust generated is submicronic, and you do not want to be breathing that in. The cell is designed in conjunction with a hood to effectively draw air into the ductwork. From there, it travels into the cartridge-style dust collector where the fume is removed by the filters. With the dust removed, clean air exits the fan and is discharged back into the facility. Your typical 4 major components to a dust collector system are the hood, ductwork, collector, and fan. If one component in a dust collection system is poorly designed, the whole system is affected. So when experts like Nate design a system, there are a lot of factors that are taken into consideration. I'll let him walk you through them.
Yeah, thanks, Alex. So as you can see, here's just a few that we would consider. So of course, the material being collected is probably the number one. We would certainly look at total airflow requirements. Hey, are we looking at ambient versus source? And, hey, do you have any future expansion? I mean, like I said, these are just a few of the application details we would look at, and certainly leading into the applications engineering team as we look at particulars for each of your projects.
Thanks, Nate. When we think about collecting dust, fume, or mist contaminants, there are some important characteristics to consider, which help us to determine the type of collector and filter media. In terms of size, some contaminant is visible to the naked eye, while other types are only visible using a scanning electron microscope. On the larger side of the scale are contaminants such as cement dust, fertilizer, coal dust, and milled flour. On the submicronic side is contaminants such as weld fume and carbon black. The size of the dust is important because it dictates how the dust cake will form on the filters in the collector. Moving on to the shape. The shape of the contaminant could be spherical or round, fibrous, think long and skinny like shredded paper, could be flaking or flat, or even a mixture of different shapes depending on what type of application is generating that dust. The photo shows fibrous particles from a fiberglass sanding and grinding operation. In this situation, you would probably need to specify a particular type of filter media and potentially a specialized baghouse to keep the dust from bridging over the outlet and in between the filters. Next, we have bulk density. Bulk density is the amount of weight that is measured in a defined volume. It is expressed in mass per unit volume, typically pounds per cubic foot or kilograms per cubic meter. An example of a lighter dust is oats at 26 pounds per cubic foot, and on the heavier side is lead carbonate, which is about 250 pounds per square foot. Do you think the same amount of airflow will capture each dust effectively? Probably not. Bulk density will absolutely factor into your capture velocity calculations when sizing a collector. Next up is abrasiveness. Abrasive dust will abrade filters and the structure of the dust collector itself. Examples of abrasive applications are sand drying, metal processing like copper slag, and other types of mineral processing. So it's an important design consideration. Nate, what would you do to minimize abrasion inside of a collector?
Yeah, it's a great question. The first thing we really want to manage is like the velocities. We want to be thinking about how are we managing the dust as it's entering into the collector. And, there's a couple of strategies that we can incorporate to help manage that, whether we're looking at, say like an extended dirty air plenum, or maybe an AR style inlet. But again, that's kind of the key there when you're trying to manage abrasiveness is how do we manage the velocities and how do we effectively manage that material going into the collector?
Thanks, Nate. Another characteristic is agglomerativeness. This is the characteristic that will tend to gather dust into a ball, mass, or cluster. Examples of agglomerative dust are paper, cellulose, and cotton. Think of it as dust bunnies or tumbleweeds. Special cartridge design or potentially a specialty baghouse may be needed if the dust is agglomerative. Next on our list is hygroscopicity. This is the dust characteristic that will readily take up and retain moisture. Hygroscopic dust examples include acids, starches, and cement. Think very dry dusts that want to absorb moisture if present. You want to keep them dry and free from moisture ingress or even humidity. Selecting the right collector and filters is important for dust that retain moisture or there's a potential to plug up the filter media. One of the last contaminant characteristics we will review is chemical composition. This is very important to consider. It's always a good practice to get the safety data sheet on the dust from the customer. This will provide some information regarding corrosiveness, toxicity, and explosiveness. These factors may affect the collector or filter media type, material of construction, and recommended accessories such as bag-in, bag-out options, and explosion suppression devices. The last characteristic we will discuss is combustible dust. I'll pass it over to Nate for more details, as this is a large topic.
Yeah, this is a large topic. We could probably spend, if not a day, maybe even a week, exploring the various aspects of this subject. But hey, we'll just take a quick snapshot so that you all kind of understand that this exists and this is something that you're going to have to address. So here on the left, I think a lot of us are familiar with this fire triangle, right? What do you need for a fire? Well, you need a combustible dust, you need an oxidizer, and you need an ignition source. If we move one step to the right, we can see this kind of flash fire square. We're just basically adding one more element to this, right? And that is the dispersion of the dust. So much like the fire, we will have a fire or a combustion event, but to get this flash fire, you need that dispersion of dust. And then finally here on the right, we have the pentagon. And this is adding the aspect of containment or confinement of the dust. And with each one of these, you need to be thinking about, okay, how am I going to effectively manage this risk? What are the solutions? What are the potential solutions here? And how are we going to do this? One of the things that I'll suggest is that as you're stepping through this, especially with the explosion risk, when we're looking at this in particular with the dust collection system, the end users are going to have their dust tested. And most specifically, we're looking for KST and PMAX. There are a few other values as well, like in the standard dust test that we would look for, like MIE, NET, some of these other features. But KST and PMAX are the ones that we would be looking at to help size and select explosion protection equipment. And now here's a few other terms. I'm sure some of you are familiar with them, but we'll just kind of brief over it. So first, airflow, usually denoted as Q, is the volume of air flowing through the system. You can see this usually here in the States. We see that as CFM, or cubic feet per minute. The second term here is velocity, denoted by V, measuring of the linear speed of the object. In this case, usually it is the air and the dust, measured in feet per minute. And then the area, typically of the ductwork. Sometimes we're talking about filter area, but just A for area. And this is denoted as square feet, not surprising, right? So if we look at the airflow calculations below, we can see Q equals VA, and then you can see how, based on the unit evaluation, you can see how cubic feet per minute equals feet per minute over, or feet per minute times feet squared. And this is going to play into the next slide here, where we're talking about air to media ratio, or AMR. This is really, it's a basic way for us to understand how aggressively or how conservatively sized a collector is. This started very much in the baghouse industry, and we look at, again, the total airflow, Q, or cubic feet per minute, and the total amount of area of the bag, and then we essentially get a face velocity. So if you look, or if you think back to that previous slide, you can see in the unit conversions that essentially, as you bring these two together, you have a face velocity, but we just reduce it down to a ratio. And again, when we look at it, we can easily say, oh, 6-to-1, that's pretty conservative, or hey, that's pretty aggressive based on then the application details. Now, can velocity usually refers to, or we're mostly concerned about this aspect when we're talking about a baghouse with a low entry point. You want to think about, okay, if I have air coming in low and it's going up towards these bags or the filters, that air is driving that dust upwards. So depending on things like its shape, its density, we kind of maybe could resolve that into aerodynamic diameter. I've heard it described before. But essentially, can velocity can play a factor in how well a dust collector works. And similarly, we have interstitial velocity. So instead of the kind of raw open area of the baghouse versus the total amount of air, we are now looking at the space in between the bags. So the interstitial velocity is going to always be higher than the can velocity. And again, this is something we want to consider when we're looking at things like reentrainment, right? How effectively does that dust pulse off of the bag and then move down towards the hopper and then out of the system? And then finally, looking at static pressure. Essentially, it's the air pressure or the resistance within the system, looking at the static pressure of the collector, flange to flange, looking at the static pressure of the hoods. What's it take to accelerate that air into that hood through the duct system and whatnot? And again, typically expressed in inches of water gauge here in the States. So a grain, this is a very small unit of mass. Essentially, it's 1/7,000th of a pound, and very common in munitions, right? When you're thinking about gunpowder, that's how they typically will measure the munitions there. But it gives you an idea, okay, here's the mass. So this is how we're describing the mass of the stuff that we're collecting at the hood, right? And this helps us then in the next piece, this grain loading. How much stuff is in the air? What's the dust concentration, or what's that mass concentration within the air? And this helps us understand, again, how conservative or how aggressive this application might be. Something with a grain loading of, say, like 0.1 grains per dry standard cubic foot, that's pretty easy, right? When we start talking about things that are like 2 or 3 grains, we're getting quite a bit more material, and we probably need to start thinking about not only how is that going to affect the filters and the filter life, but then how are we going to manage that material throughput, right? Do we need to consider things like pneumatic convey? Do we need to consider things like maybe a trough hopper with a screw, right? So it kind of helps us to widen our scope and better understand the application. The filter media, of course, very important. We want to think about how that dust is going to interact with that filter media. Say if it's a oily type of dust, maybe it's a grain, maybe we look at an oleophobic treatment. If it's fibrous and we're looking at a cartridge, maybe we want to open those pleat spaces up so that those fibrous materials don't get plugged within the pleat. And then finally, the dust cake. This is that layer of dust that is formed on the top of the media. And this actually contributes to the overall performance of a system. The better we can produce a dust cake, the more effective we can be. And essentially, we're keeping that dust on the surface. And I know I don't mean to steal Alex thunder, but it's hard not to talk about that. So I'll kind of leave it at that and let Alex take that up when he gets to his time. So let's start with the collectors. Let's start with the overall dust collection systems and kind of the main 2 types. So, oh, sorry, I'm jumping ahead. Let's talk about our objectives, right? So we're delivering a sufficient and effectively while operating in a predictable, stable, and economic fashion, right? We want to know how the dust collector is going to work, right? We want to make sure that the end user is able to account for that and that they can plan for that, right? They don't want to have these upset conditions where they have maybe additional costs, or maybe it's not sized correctly and they're having issues with pickup, right? And some common mistakes with that are, first and foremost, poor assumptions, about the application. We didn't understand the dust, maybe didn't understand the total system correctly, and that can lead to problems down the road. Certainly wrong filtration technology. If we have a dust that is, say, oily, and we put an oleophilic filter on there, well, that's going to blind off pretty quickly. So we want to make sure we're really understanding the filtration mechanisms, the dust types, and picking the right filter. If a collector is incorrectly sized, it's a tough place to be, right? You don't have many options. So we want to make sure that we're sizing it correctly right up front. And of course, the dust collector sometimes, many times, gets blamed for all of the problems, but it could be a poor installation as well, right? There could be some other system effects upstream or downstream that could be causing overall system issues. So we want to have, again, this kind of broad scope from hood all the way to fan outlet, making sure we understand, what those parameters are so we can have a very well run system for the customer. And now here, this is what I was meaning to get to, the 2 different types. Cartridge collectors. We have cartridge collectors on the left, bag houses on the right. And these are kind of the main 2. We'll get into a few other specialty types as well for certain applications, but let's start with these. So the cartridge collector, introduced by Donaldson in the 1970s, certainly a lot smaller than a bag house, provides some inherent value just in that, certainly lower cost initially. it is also quite a bit easier to do a filter change out. I've done both, and I can tell you I would much rather do a cartridge than a bag. The bags are dirty, take a long time, relatively speaking, and certainly cartridge provides some great value. Although there are some things that maybe would prevent us from getting into a cartridge, and we'll talk about that. But this is best for uniform dust, dry and free flowing, and that's kind of the main thing that was pounded into my head when I was in the applications team is, hey, what's the dust? Is it dry and free flowing? Does it seem to be kind of acting appropriately? Then a cartridge is probably a good place to start, right? That's kind of our first thought in the hierarchy of making a decision. So some markets, fabricated metals, food processing, kind of depends on what the food is, right? But some food processing pieces, pharmaceuticals, minerals, and a whole host of others. So here's a couple of examples. On the left, we have laser cutting, and it's pretty simple. I mean, can't see the hood, but the hood is in the building. It has a ductwork, comes into the inlet, into the collector, and then just out the fan. Doesn't appear to have any kind of explosion protection on it. And it's really kind of a simple, very elegant solution. On the right, we have powdered tea leaves, and you can see this large mass on the left side of the collector. That's a flameless vent. That is essentially an explosion vent, which is also covered by this stainless steel wire mesh. And that wire mesh helps to knock out the flame front. It will not knock out the pressure wave. It helps to relieve the pressure, but it will knock out the flame front and provides us an opportunity to put a collector, say, inside when you may not otherwise be able to do that, right? There's kind of two solutions for that. Skipping ahead a little bit, but there's the flameless vent, and then there's also a suppression system. Essentially, the suppression system is a sodium bicarbonate filled bottle, and then it'll discharge into the collector to snuff out a combustion event. But those are kind of the two we look at when you're going inside with a combustible dust. Here again, plasma cutting, another thermally generated dust. Very common to see the cartridge on this. You can see the dust collector in the background. And then on the right, a metal grinding booth. So right here, we see the booth, and you can't immediately see the collectors, but there in the back, there are 4 sections of louvers, and that's the bottom of our DWST. And so that is a kind of point of use collector, great for booths. Just provides some flexibility as well. So, it's not always that kind of traditional cartridge that you're thinking of. We can incorporate this into some other spaces too, if the need would present itself. Here's some more welding examples. You can see in the background on the left, quite a bit smaller. Those can go inside, the ductwork is running under the rafters, and then you have now your pickup, your extraction arms there. And then on the right, you can see a little bit bigger, headed outside, and it just kind of shows you, hey, the kind of the breadth of what Donaldson can provide in terms of size and scope. And I'll pass it back to Alex to talk about particulars on filters.
All right, thanks, Nate. Yeah, it might be obvious, but cartridge collectors use cartridge filters. They come in a variety of sizes and shapes depending on the type or style of the collector. There are a variety of cartridge filter medias available, and I'll share some details on why you would choose one versus the other. So first off, I want to cover one important filtration concept with you. A famous phrase around here is that dust filters dust. As a dust cake builds up on the filter, it increases the efficiency of the filter, meaning it captures finer dust once that dust cake is built up. Filters within a dust collector are going to get dirty and get dirty quick. Not all filters create a dust cake in the same manner. Ideally, select a filter with surface loading technology. This will increase your filter's lifespan, allow you to use less energy in the form of compressed air and horsepower of your fan, and reduce your overall emissions. So if you look at the photos in the bottom right, you can see the SEM image of a clean surface loading filter next to a dirty one. It's that nanofiber layer on top of a media substrate that holds the dust on the surface of the filter. So here's an animation demonstrating how surface loading technology works. You can see the dust is held on the surface of the filter. and not allowed to embed itself into the filter media. This is what we call depth loading, and you'll want to avoid this. Surface loading allows the dust to pulse off the surface of the filter, and that in turn leads to a system that runs at a lower pressure drop longer. You can see the animation just started now. But that will maximize filter life and reduce your energy use. So there are a lot of things to factor in when selecting a filter for a cartridge dust collector. To name a few include temperature of the application, moisture, and all of the dust characteristics we reviewed. Really, you want to think about the dust and how it will interact with the surface of the filter. It has to have the ability to capture the dust and be pulse cleaned while in operation. It also has to be able to hold up to the temperature and any chemistry within the process. So I'll explain a few different types of cartridge filter media options. First up is UltraWeb. This is our trademark nanofiber media I mentioned before. The nanofibers are laid on top of a cellulose or paper media, similar to what your car air filter would use. An overwhelmingly majority of installed cartridge collectors use UltraWeb. Works great on light, dry, free-flowing dust. It can also handle submicron dust like weld fume. Other applications for UltraWeb are pharmaceutical powders, carbon black, and thermal spray. The next media I'll review is Toritex. Instead of a cellulose-based media, it uses spunbond polyester. This is a fancy way of saying plastic. What makes this special is an expanded PTFE membrane that is laminated to the surface. This provides a smooth, slick surface that can repel water and hold up to chemicals. Toritex is also very efficient, meaning it can capture very fine dust. Overall, think of it like the Gore-Tex in your rain jacket, or it makes a cooking pan non-stick. It's commonly used in chemical processing, food applications, and for paint pigment manufacturing. The final one I'll review is our high temperature media. This is made of aramid fibers, a silicone gasket, and silicone glue that can withstand very high temperatures up to 350 degrees. Its performance is in the name. This is used in processes that create heat like process dryers, kilns, and coal combustion. So these are just a few examples of cartridge medias that are available. There are a variety of others available to meet the needs of a given application. We have a lot of resources available online, as well as a team that can help you select the right one for your application. Shifting gears, Nate will be reviewing baghouse collectors next.
Hey, thanks, Alex. Yeah, so the next is bag houses. I'm sure that many of you have seen these out in the industry. But right here, we have an example of a Donaldson RF collector. They're certainly better for high grain loadings. These are the workhorses in the industry, of course. They're more forgiving on more challenging dusts. And this is really mostly in part because of the mechanical action that you can get out of a bag as opposed to a cartridge. When you send that pulse of air into a bag, it expands and it has this bit of a snap action. And that is actually what's very helpful in these more challenging applications. You don't really get a lot of mechanical action in a cartridge. These baghouses are certainly larger in size, although we do have some smaller ones. They are more labor-intensive filter changeouts in traditional bags. I'll let Alex talk a little bit more about some alternatives here coming up. But most of the markets that we serve here are like, woodworking, grain, cement, sanded paper, food even, right? We talked about maybe salts and sugars and whatnot. So certainly a great workhorse within the industry. So here's a couple of different examples of dust collectors, so particularly bag houses. An onion processing facility. You can kind of see scope and scale here with that car in the foreground. You see you got a trailer underneath the hopper and the discharge there. And I can see what appears to be explosion vents on this collector. And so you can just see kind of how wide and varied we would get into. Certainly onion processing, not something I normally think about when I think of dust collection, but there it is. The other one, skateboard manufacturing, something maybe more traditional, right? Probably more woodworking, right? Also has explosion vents on it. And again, can kind of show you a little bit on the variety of where these bag houses can serve. Now, this next one on the left is our MB or modular bag house. This is more of a traditional rectangular modular style bag house. Can get quite a bit larger if needed to, but this one has a trough hopper and looks like a live bottom hopper there with either a screw or a very wide rotary airlock. And then on the right, you have a grain processing facility. You can see this up on a big kind of mezzanine structure here for that grain processing facility. And again, can just show you kind of how wide and varied these things can get into. And back to Alex to talk particulars on bag house or bags for bag houses.
All right, so bag house collectors use bag filters. The two main types are fabric bags and pleated bags. Fabric bags are installed over metal cages. During filter changeouts, the entire bag and cage are removed from the collector. The used fabric bag is removed from the cage and the new one installed in its place, then goes back into the collector. So imagine having to do that a few hundred times. Messy, dirty, cumbersome process, right? On the other hand, we've got pleated bags. They're a one-piece design. They eliminate the need for a cage and a bag. They tend to be shorter in length and take significantly less time to change out. Because the media is pleated like a cartridge, they offer 2 to 4 times the filter media as well. Not all bag houses can use pleated bags, but they are a problem solver for troublesome applications, such as those with abrasive dust. So when selecting the proper media for a bag house, it's very similar to that of a cartridge. The applications and dust characteristics will be different, but you still need to answer the same questions. How will the dust interact with the media? How will the dust interact with itself? There are media types available to tackle challenging dusts if all of these factors are considered in the selection process. So the first bag filter media I'll review is Duralife polyester. This is a go-to media option for a majority of baghouse applications, designed for dry, non-abrasive dust. Works great on grain dust, fine wood dust, and flour. This is the first media consider when designing a system. If the dust is more challenging, you'll want to take a look at some other options. So the next one of those I'll review is Duralife oleophobic. So this is our standard Duralife polyester that has been treated to repel oils and moisture. It can handle wet, oily, and sticky dust that would plug a standard media. A few applications you'll see this on are nut processing, oils, or any process with oils or hydrocarbons in it, or soap. The final bag I'll review is Aramid. This media is identifiable by its yellow hue. Aramid fibers are also used in firefighting gear to protect firefighters from fire or heat. It's useful as a media for filter bags as it can handle high temperatures up to 425 degrees Fahrenheit. A few examples of those applications are cement, asphalt, and steel. This is just a sample of common medias for baghouse style collectors. There are a whole host of other media options that will depend on what the application demands. Again, we offer resources online or via the phone that can assist you in selecting the right one. So I mentioned these earlier, but pleated bags are the other filter option for a baghouse dust collector. If you're looking to avoid common baghouse issues before they start, pleated bags are the way to do it. They'll replace standard fabric bags and cages in your baghouse with no modifications. The benefits of pleated bags are that when applied right, you'll eliminate filter abrasion, like in abrasive applications, say like sand drying. They will lower emissions. Who doesn't like cleaner air? I mentioned they add filter media to the collector. Again, typically 2 to 4 times. It all depends on the situation. But that added filter media will provide longer filter life, meaning fewer filter changeouts and less production downtime. Not only will they need to be changed less often, but they take less time to change them out as well. Lastly, you can turn the system's pulse pressure down when using pleated bags. This provides energy savings in the form of reduced compressed air usage, generally about 30%. So if you want to optimize the performance of a baghouse, pleated bags are a great option. So now that we've covered baghouse filters, Nate is going to review some specialty collectors with you.
Yeah, so here's another collector that we can consider. So sometimes you have applications where maybe it's really hard to get a hood or a ductwork piece into a particular location. Each one of these red arrows is showing the location of Donaldson CPV. So you can see that these are really point of use collectors, right? So it's taking the dust off of, that particular location and then actually putting it back into the system right there. There's no hopper on this collector. It's just collecting and then reintroducing that dust. And certainly you can see the advantage and the value in having this kind of point of use collector. I mean, think about having to run ductwork from each one of these locations on this articulating, structure, and figuring out how to get that all to work well while sending it to a single dust collector. That certainly provides some particular challenges. Right here for these, all you need to do is run power and then compressed air, and then you can service particular locations. So certainly a great advantage to keep in mind when you have something kind of challenging. And this other collector is actually a bag house, but it's certainly under the specialty collectors category. This bag house, as you can see from the animation, provides a significant amount of mechanical input to help manage dust cakes that are particularly challenging. Um, I'm always reminded of a story from Gabriel Safarian, who was one of the engineers there at Donaldson, and he was on site troubleshooting a collector. It was on sugar dust, and the bags, they got caked up with all this crystalline structure of the sugar, right? The pulse cleaning actually wasn't set up correctly, so the bags just got loaded up. And after they had realized what the issue was, they corrected it and then sent it through a pulse cleaning sequence. And there were sheets of sugar coming down and crashing in the collector. And they turned the fan back on and it worked great. So again, really a testament to this technology. But if you have a challenging application, whether it's, crystalline or sticky or maybe particularly agglomerative, uh, you know, there's an option to consider for a bag house for those particular applications. And here's another specialty collector. We've talked very much about dry collection, but Donaldson also can address any mist collection needs that might be out there for a customer. The WSO particularly stands for water, smoke, and oil, and is a solution that you can apply, on say like CNC routers, right? When you have water soluble coolant on cutting or oil, in a flood bath for cooling. And then sometimes we even see thermally generated droplets, and these are usually that blue haze that you see, right? If like you think about a car, it's burning oil and it's got like this blue haze coming off the tailpipe. That is a thermally generated droplet, and that's what we can help address here as well. So if you have particular manufacturing processes that produce that type of droplet, then think about a WSO. That might be helpful. And then also ambient collection. So these are cartridges. This one on the left is AT3000, ceiling mounted type of unit. It helps to produce, say, what we have called a racetrack within a certain area. So usually this is in conjunction with other AT3000s set up within a space. And really the name of the game on ambient collection is effective changeovers within the space. So if you have an ambient system that you're working on, it can be somewhat difficult, but try to get as many good changeovers within that space as possible and should have a very effective solution. The other thing to consider is this DFA tower. So unlike the ceiling mounted, you could have a tower style, kind of, tall and skinny. These could be located within certain areas of a facility and to help provide that overall kind of dilution effect that you're looking for. Ideally, you'd be setting up some recirculation zones and kind of looking at that. But again, that's a wider conversation, really kind of for another time. But things to think about are what are some big obstructions maybe within the space? What other cross flows could be happening? Could it be coming from fans? Could it be coming from any kind of fork truck traffic or doors opening? But those are the things that I would consider when looking at that type of application. All right, so we are going to go through kind of a quick Q&A with you guys, a little bit of interaction. We are going to just ask you to maybe agree or disagree with the spec that we're going to throw at you here. So the first scenario is for an application with paint pigments. So it's a mixing application. The dust is dry or submicronic. We kind of have this, maybe medium grain loading, and the airflow is around 10,000 CFM. So what do you think? Agree or disagree? Thumbs up, thumbs down. What do you think about a baghouse?
Looks like I'm seeing some agreement with the baghouse.
Yep, I'm seeing agreement, disagreement. Yeah, see, I'm seeing mostly agreement. And here are my thoughts, right? I don't think a baghouse is necessarily wrong. However, I think a cartridge would probably be a better fit, only because these paint pigments are usually dry and free flowing. And unless you're getting into something in particular with kind of a specific material challenge, cartridges have proven to be fairly successful in this application. Again, not to say a baghouse wouldn't work. A baghouse certainly would work, but I just think that a cartridge probably, is a slightly better solution for that application. All right, here, scenario number 2, a Banbury mixer, carbon black and additives. It's going to be oily and submicronic. Again, a medium grain loading, and we got about 20,000 CFM. What do you guys think about a baghouse? Do you agree or disagree?
Right. Looks like I'm seeing mostly agree on this one.
Yep, that's what I'm seeing too. And I would agree with that as well. I think a baghouse is the best first selection on something like this, particularly because of the oily issue. I think, this dust is probably going to be a bit more challenging. We probably want to have that mechanical action from a bag to help address this need. All right, scenario number 3, a robotic welding cell. So we'll have a thermally generated metallic weld fume, submicronic, probably a light to medium grain loading, and about 8,000 CFM. What do you guys think about a cartridge?
Yeah, looks like we're agreeing with the cartridge.
Yep, that's all I'm seeing. I think these guys are sharp. So I would totally agree with that as well. This is absolutely cartridge all the way, unless there's something that would maybe crop up in some other kind of application details. This is absolutely a cartridge. Yep. All right, scenario number 4, a coating application for sugar dust. The dust is described as agglomerative, also medium grain load, and the total airflow is about 7,000. What do you guys think about a cartridge?
So some disagreements with the cartridge.
Yep, they're sharp. I can they're sharp. Yeah, I would agree. I think a cartridge is not the correct selection here. I think a bag is certainly the first thing we would want to consider for this kind of sugar dust or any kind of like similar food applications. That's probably where we would start. And then how about scenario number 5, a truck pit or a receiving pit for trucks, corn dust. The dust is dry and free flowing. Again, kind of medium to higher grain loading, 12,000 CFM. What do you guys think about a baghouse?
Again, mixed. We're getting mixed.
Yep. I'm seeing mixed reviews. Yep. Yeah, I think, we want to know a little bit more about the applications. I think we probably need to ask some more questions. I would probably lean into baghouse on this one. But again, I would want to ask some more questions just to better understand what it is that we're going to be getting, how that might interact with the collector, and if we see any problems with the cartridge. All right, so we've talked about some general kind of like, okay, which way do we go, bags or cartridges? Now we're going to get into more like sizing, kind of showing you, hey, how would we do this, right? Just simple examples. Certainly, we're here to help if you guys have any particulars, but we'll jump into a couple of examples to kind of show you guys how we would do this. So first and foremost, we want to be thinking about AMR, right? And there are particular AMRs for each application. So we need to be asking a bunch of questions, including how aggressively do we want to size this? And Donaldson certainly has AMR guidance. So one thing I want to exemplify is particularly on the cartridge, we can have the same dust type right? A thermally generated metallic fume. It can come from a fiber laser or it could be ambient weld fume. It's essentially the same dust, but depending on how it's presented, we might tailor that AMR very differently, right? A high powered fiber laser is a fairly aggressive or fairly challenging application. So we would want to be more conservative in that. We would be closer to that 1-to-1 on that high powered laser versus say like an ambient weld tube. There's a lot of dilution air within that capture. And so we would run that collector very aggressively. We would try to size that quite a bit closer to 4-to-1. Now there's some other things that we would consider as well. And again, I won't get into that, but we would size that pretty aggressively. And then similarly with a bag house, um, depending on the application, like say a diaper fluff or like a super absorbent pulm or whatnot, we would run that one, very conservatively and do some particular things to the configuration. Whereas say like a small wood shop, that's not running 24/7, maybe it's like a high school, right? We would run that probably more aggressively because again, the dust challenge just isn't there. And so things to kind of consider, right? Like what happens if we're too conservative? What happens if we're too aggressive, right? Well, too conservative, they get extended filter life. That's not necessarily a bad thing, but there are increased operational equipment costs up front, right? That's going to be higher capital spend right away. When you're too aggressive, you can have shortened filter life. That's an ongoing cost. You would have insufficient airflow, and we're maybe not even solving the reason that we were brought in the first place, right? We were brought in to help them solve their dust collection needs. And if it's too aggressive and you don't have sufficient airflow, you can't get effective capture at the hoods. So, there's additional operational costs associated with that, more interacting with the collector. You want to strike that balance, right? And so we don't want to be too conservative and we don't want to be too aggressive. And that is exactly what these AMRs that we're going to look at are going to help us with. So this first example, a fine dry dust from cutting and sanding. The grain loading is high, so we kind of know immediately we're into a bag house. 15,000 CFM, and the recommendation is about 8-to-1. So to get there, we would look at 15,000, we would divide it by 8, and then we get that about 18, almost 1,900 square feet of media. So we would go to our chart and look at, okay, well, which models of the Donaldson RS would provide that amount of media? And so we're somewhere between kind of this, 146 and the 156. The 146, that has about 1,900 square feet. So we do have a little bit more media there, just a little bit, versus the 156. But the other thing we would consider, and not immediately probably known to the audience here, is that the 146 and the 156 share the same can size. They're the same diameter of dust collector. So there's probably some efficiencies within the economics of it all, right? To say, okay, well, it's probably not that much more to look at like a 156. So how does that shake out? Like, what does that mean for the customer? What does that mean for the application? How do we make sure that we're asking the customer the right questions? Like, what's most important to you? Well, how can we best serve you with this selection? So those would be some of the things that I would look at immediately. And then similarly, we have a fine, dry, free-flowing dust, kind of medium to low grade loading, and we would be about 15,000 CFM again. But at this point, we would be at an AMR of 3.5-to-1. So similarly, we take our 15,000 CFM and we divide it by 3.5, and we get about 42, almost 4,300 square feet of media. So then we would look at, say, like a DFE 416 or a DFE 318. And again, we have that similar conversation where, the 416 is pretty close, right? I mean, we're pretty close to 4,300, not exactly, but that AMR would go up. And so we would want to think, okay, well, we would need to know more about the application. How aggressive do we think that we can be? Or, is the customer willing to interact with the collector a little bit more with a slightly shorter filter life? Or would they prefer to have a little bit more filter life with that 45, almost 4,600 square feet of media and maybe goes with a slightly larger collector? Ultimately, we're here to help, right? So let us know what your questions are. Let us know how we can help you with particulars as you're interacting with end users and designing systems. And so you got, particular question like, hey, what do you think about this inlet configuration? Or this dust is agglomerative or it's sticky. What do we think about that? Certainly, we've been doing this a long time. We got a great team behind us in the applications and the product management team. So, again, let us know how we can help. Let's start that conversation.
All right. Hey, thank you. Great job, Nate and Alex. We're going to finish up with some Q&A. Trainers, if you turn your cameras back on now. Just heads up, everybody that attended will receive an email with your professional development hour credits. There's also a few QR codes here if you're interested, including our events page for other live upcoming webinars. Next month, we'll be focusing on fan design. We also have a library of on-demand webinars from past recordings that you can view. If you have follow-up questions or if you don't get your PDH credit, sometimes it winds up in your spam folder here. Just send me an email and I'll make sure it gets out to you. Also, in case you aren't aware, we are doing a 5-hour training in-person classes on system design for engineers in select cities over the next few months. We just had one in Atlanta, Georgia. We'll be heading to Dallas, Texas in January. On January 28th, Toledo, Ohio on February 4th. And there's a link here for more information, or you can send me an email to learn more about that, where we go a little more in depth and we have, again, in-person training that gets deeper into all the areas and aspects of dust collection. So with that, I will have Amy start us off with our first question.
All right, thank you. And John, would you mind posting? We're going to post a link in the chat box with a link to information if you are interested in registering for the in-person session. I can't do it myself. John, if you could do that, that'd be awesome. Thank you. Okay, so anyway, here we go. Let's get to some of the questions. All right, when using dust collection system and recirculation, typically the AHJ or the authority having jurisdiction will require a HEPA filter as a secondary filter. At what point do you become uncomfortable with recirculation based on dust and fume hazard level?
Yeah, I'll take that one. So first and foremost, Donaldson wouldn't provide input on, them being comfortable or not comfortable with particular levels. This is up to the AHJ and the design engineering team. What we can do though is we can provide you with the kind of the expected emissions level, right? An emissions statement based on different filter types. So in brief, like a cartridge is typically rated for 0.002 grains per dry standard cubic foot. So that would be an emissions kind of level that you should expect, and then should go into the calculation of how to present that back into the building. Now, if you're also adding a HEPA on top of that, that is just kind of further, refining that airstream, right? And so all that would have to be taken into consideration. But Donaldson can't necessarily make a call to say, yeah, we're comfortable with this or that. We would give you the tools to be able to help you answer that question.
Thank you, Nate. Next question they're asking is, does can velocity apply to a cartridge collector?
It's an interesting question, and it kind of ties back to what Alex and I spoke about very early in the conversation about abrasion, right? So when we're thinking about can velocity, again, this is something we're looking at for kind of lift, right? Like as dust is going into a collector and the air is pulling it up towards the filters and it's coming down. That doesn't really apply with a cartridge, right? Because our cartridge collectors are downflow. What I would say is we would look at internal velocities within the cabinet to help understand, do we think that there's an abrasion potential, right? And how would we effectively manage that? So again, I don't think it's going to apply in the same way as, say, a traditional baghouse.
Thank you. Next question, probably for Alex. What's the best filter media for lead emitting smelting?
Oh yeah, this is a great one. Challenging application. I'm guessing there's temperature involved. Probably want to look at a specialty media, something that can handle the temperature. Probably depends on what that temperature is. Something that can handle the chemistry. I think standard polyester singed filter will probably get eaten away by just some of the chemicals in there and the chemistry. So I think looking at some of our specialty filters would be what you'd want to do. Probably something with a PTFE membrane, give it surface loading, added efficiency, maybe even like a PTFE felt with a PTFE membrane. That's probably your ultimate solution, but they'll all vary. And if you want to learn more, we could dive deeper into that situation.
Yeah, we would need to know more about the application in particular to be able to make a good selection, but all those things sounded really good.
Thanks, gentlemen. All right, next question. Nate, I'm assuming this one's for you. Can you change the direction of airflow on a cartridge collector?
Well, I guess I don't totally understand the question, but essentially no. And before I say yes or no, let me let me describe a little bit better. So the airflow is typically outside in, right? So the air is moving from the dirty air side across the outside face and then into the inner part of the filter and then moving into the clean air side. Can you change the direction of airflow on a cartridge collector? We do this when we're pulsing the filters, right? So on a multiple cartridge unit, we're looking at pulsing maybe just a fraction of the total, and we do send a reverse pulse jet in there. So can you change the direction of airflow on a cartridge? Yeah, I guess in that respect you can. Don't know if I totally understand the question, but hopefully it provides some insight. But essentially, yeah, the airflow is outside in,
Well,
and that's how
it'd
we
also be the question we ran to the inlet, where you're coming in, top, bottom, side, you can change that.
Yeah, there's that too. Yeah, you could change depending on certain types of inlet styles. You could change how the air enters in the inlet section. So that's another good point, John.
All right, so Nate, this is a kind of a specific combustible dust or NFPA question. How do you mitigate a zone 22 around the barrels or when removing cartridges when dealing with combustible dusts? Do you have a standard practice? So a zone 2 around the barrels or when
Yeah,
removing cartridges.
like a class 1 div 2. So class 1 div 2 is gas not normally present, right? So
Well, actually, okay, so
uh,
this one was amended. So they changed it to zone 22 class 2
I see.
in the
Okay.
next
Oh, I
comment.
see it
Yep.
down there. Yep. So zone 22, that is typically like ATEX. Like if I read that correctly, and the parentheses now showing class 2 div 2. So class 2 dust, div 2 not normally present. How do we manage that? We would have to have a conversation. I don't know if I'm comfortable answering that question just off the cuff like this. I need to know more particulars about that. I would want to pull the applications team in. But so Jamie, if you're still out there, please send us a note and let's make sure we get you connected to the right person or team, right? I want to make sure because there's a lot to be handled here, and I want to make sure that I'm not just kind of giving you an off the cuff answer for something that's got some pretty big implications.
We'll make sure and reach out to the person that asked the question to make sure that
Okay,
that they're able to get the answers that they need. Thank
great.
you. I wasn't sure about that.
Yep.
Next question. How do you estimate the grain loading for sizing a filter for a new process where customers don't know how much dust it's going to generate?
Yeah,
Great question, right?
that's a great question. That's a tough one.
Yeah.
So let me kind of start most generally, right? The better job you do with your footing, the more dust you should be picking up. Depending on the process, we could make some assumptions based on, kind of what's happening, right? If you're doing a grinding or if you're doing, say, like a rabbet cut in like the wood industry, right? You would know essentially how much kind of material you're pulling off of, and then you should get an idea of that. Now, we would also have to know all of the system pickup points so that we could add those up and then look at total mass to total CFM and then get your grain loading. That's how I would start. It is a great question. Let's also put it this way. You could back calculate, right? You could say, okay, what if I assumed that they had, say, 2 grains? Well, what does that look like in terms of total amount you'd have to know a bit of density, right? You'd have to know what the bulk state was for that dust. But then you could back into like, okay, well, how much am I going to get within like a day? Is it going to be a 55-gallon drum or is it going to be like a 54 cubic yard hopper, right? And you go, okay, that seems reasonable or not reasonable based on my understanding of the process and the dust and whatnot. So that's how I would start, right? I would try to start generally, and I would try to pare it down further and further, kind of challenging the application with the end user, and then saying, hey, do we think that that is what we're actually going to get? And then you can start to kind of have that conversation.
One of the nice thing is our application engineers, I mean, we have a library of decades of,
Mhm.
sizing equipment, so we can kind of go back and take a look at some historical similar applications and try to make some
Yeah.
of those assumptions, right?
Yep. That's a great point too. Yep.
So Alex, it looks like this next one is for you about Toratex. Are there any upcoming changes that you're aware of to remove the PFAS or PFAS from the Toratex product?
Yeah, good question. We have a very large and well-funded corporate technology team. This is a project they're working on. I don't really have any specifics I could share, even that I know, but it is something we're looking into.
All right. Darn, I was hoping you could tell us something. I wasn't sure either. Thank you for the information. Okay, so we talked about high temp previously. So this actually may be the same person that asked this. So when the airflow exceeds, let's say 480 degrees Fahrenheit, what do you do? Like, is it best to cool it with a heat exchanger or bring in outdoor air to mix in and lower that temperature? Because 450 was kind of maxed out, right, Alex, for even the highest temperature? Like, what do you guys recommend for what do you do if you're in that 480 range?
In terms of filters, there are a few options that go up to 500, but if you're exceeding that, you'll probably want to look at one of these other options. Maybe Nate has more info on which should be the better route to go.
Yeah, we have recently worked on kind of preliminary application with a customer who is pulling off of like a furnace, right? And they did have to do cooling, and they were looking at a heat exchanger, but we did also look at just bringing in cooling air and mixing. Some of the things you'll want to consider is um, if you have, say, like an acid stream because they're so high, and again, I don't know particulars of your application, but whenever we're looking at high temperatures, we want to be thinking about chemistry, and we also want to think about what could potentially precipitate out, right, as we drop that temperature. So that would be something that I would consider, but I have seen it kind of both ways where, it's either just outside air or the heat exchanger itself. But again, we would need to bring it down to get into kind of a better range. The other thing is there's some economics associated with this too, right? Like as we cool, what does that look like for total volume of air or ACFM? And then what does that look like also as we look at the filter types, right? We might be in a really extravagant filter type when we're really high in temperature. But if we can cool it and there's no kind of negative effects, then maybe we get into more like standard. Maybe we get into something like a thermal web, which is something we didn't really talk about, but it's kind of a half step between our standard and the high temp. Maybe we can get into that kind of 275 range, 275F that is, and maybe that's a viable solution. And we get an ultra web on it, and so I think there's a lot of options here. We just, again, kind of need to know more about the application details.
Thanks, gentlemen. So we are a couple minutes over time. Do you guys have a few extra minutes to answer a couple of remaining questions?
I got a few more minutes.
Okay. So thanks. If you have to drop off, we totally get it. We're going to make sure and record the full Q&A session. And then we'll also reach out to those of you who ask questions just to make sure that you were able to hear the answer in case you had to drop off. So the next question is, please elaborate on the CPV. So I'm curious about that point of use. These aren't collecting dust, just pulling a negative on the enclosure. What industries and regulations require this, or where would you consider this?
My apologies if there was a misunderstanding there. These are pulling dust. So it looked like from that slide that we had, there were a couple of points. There was probably a couple of transfer points, and then there were a couple of belt conveyors. So these are picking up the nuisance dust at those locations. And then it's pulling the dust in, and then it's actually delivering that dust in a bulk state back into, say, the belt or whatnot, whatever it's serving. So that's the main intended use for like a CPV, at least in that application. We could also apply this onto, say, like a silo for a venting application. Could be passive or active with a fan or no fan. But that's kind of where we see these CPVs typically installed. But yes, they are certainly pulling dust.
Thank you. When designing a push-pull system, I assume that you would follow the same design criteria if you were just designing the dust collector as a standalone.
Um, Again, I'd like to go back to Kurt Boston and just always incorporate it. It depends, that's just kind of like the catchphrase here for Donaldson, right? Um, it totally depends, right? So when we're looking at a push-pull system, a lot of times we're looking at a larger space. Maybe there's some obstructions, maybe there's a crane, maybe there's, a few other items that would maybe provide a challenge to getting a centralized ducted system in there, right? So push-pull, if someone's not familiar, you're pulling with a hood on one end of the building, you're bringing that to the dust collector, and then you are re-delivering or redistributing that air on the other side. So then you're getting this flow across the building, right? So you get this general kind of flow pattern. And that is to essentially capture the dust. You're kind of doing an ambient collection on that. So in many respects, it does depend on a lot of these other pieces. Um, would you design it the same design criteria as if you were just designing the dust collector as a standalone? I don't totally understand that question, but um, the other piece is if you were doing it as like I'm going to assume standalone means you're pulling it as source capture. That's going to be a little bit different, right? It's going to be quite a bit different, actually. And then those
Yeah, so it's
MRs
more
would
like an
change.
ambient versus a source, right?
If that assumption is correct, then yes, right? It would be, this. Um, Yes, push-pull is really an ambient stylus system. And if you're looking at, say, traditional source capture, then your AMRs are going to shift because of that difference in application.
Thank you. Are the cartridges reusable, Alex?
So cartridges are cleaned online. They're going to be, the entire time they're in operation, they're being cleaned. We do not recommend cleaning them. There are ways you can do it. I mean, you run the risk of taking those out, damaging the gaskets. I think there's a lot of risk in cleaning cartridges. We always recommend, hey, once you've reached the end of the filter's lifespan, usually around 6 inches of differential pressure, you just want to go and change those out. If you do try and clean them, you just want to be real careful. All the gaskets are still intact. None of the media is punctured. If it's something short to get you by, sure, blow it out, throw them back in. But generally, once they hit their end of life, it's time to change those out.
Thank you, Alex. So we'll answer one more and then we'll make sure and reach out to people to make sure everyone's questions were answered. I think I got them all. What's the typical fabrication lead time for bag houses and cartridge collectors, Nate?
I think we recently published, like for cartridges, Baldwin. I think we're kind of in that 10 to 11 week lead time, and that would be kind of conservative, right? We're considering specials there too, so any kind of custom design. And then I've seen a fairly wide variety out of Nicholasville. I haven't looked at it too closely. Those are supposed to be coming out today, but like the bigger bag houses are quite a bit longer. But we'd have to look at that and want to reach out to Christian here to make sure we're answering that effectively.
Thank you. Oh, you know what? There's one more question.
Yeah.
What instrument technology do you use to measure
Hmm.
flow in large ducts used in collection systems that would suffer from plugging from the entrained dust?
Yeah. So a lot of times we're going to look at using the system static pressure to give us an understanding of what the velocities are through that ductwork. So um, very briefly, I know we're over, but you would want to look at a minimum carrying velocity for the dust. And then as you go through the setup, you would typically use like a pitot tube or like a hot wire anemometer. Kind of, there's a couple different things as you go through your setup. And then once that's set up, you would know the velocity through that duct. And then as that velocity changed, say the velocity went down, then your static pressure is going to go down. Well, we can measure that static pressure continuously. And actually, there are systems out there that would take that static pressure, run it into a control module, and then you can run it off of VFD. So then you say, okay, I want my boundary limits of like, upper pressure and lower pressure. And then if it's anywhere between there, I'm fine. If it goes too low, I need the VFD needs to tell the fan to ramp up higher, correct for that, and then ensure that you are within your acceptable range for velocity. So very crude kind of, answer to that question, but there are ways to do that. where then you're not actually going to be entraining that dust into the system.
Excellent. Thanks, guys. Thanks for staying over a little bit. Thanks for those of you that hung on with us to the end. We'll make sure the recording is available as soon as possible, and we will follow up to make sure everybody's questions were answered. Have a great rest of your day. Thanks for joining us. Thanks, guys. Great job.
Hey,
Thank you.
thanks everybody. Have a great day.
Thank you.
Bye.